Welcome to Clarity in a Messy World, the podcast that looks at the causes behind the most confounding issues of our time. I'm David Wayne Callahan. In every episode, I'll be speaking with experts who will share their knowledge and insights and help us to untangle a seemingly chaotic world. Clarity in a Messy World is a production of Bocconi University, Milan, in collaboration with the Bocconi Student Media Center. We think we know artificial intelligence. After all, we've seen it so many times in movies, often in the form of an evil, all-knowing, all-powerful overlord. This idea is both chilling and captivating, but is it true? As AI becomes a common presence in our society, what will it actually be capable of doing? Are we going to be overpowered, or rather, underwhelmed? A theoretical physicist by education, Riccardo Zecchina holds the Vodafone Chair in Machine Learning and Data Science at Bocconi University. His research explores the intersection between computer science, information theory, statistical physics, and computational biology. He's the recipient of the 2016 Lars Onsager Prize, presented by the American Physical Society. At Bocconi, he's the director of Art Lab, the Artificial Intelligence Laboratory. Riccardo, thanks for joining us today.
Thank you very much for having me on your show.
Riccardo, so many films and television series have teased us and terrified us with stories of artificial intelligence taking over humanity. Remember the computer HAL from 2001, A Space Odyssey? This mission is too important for me to allow you to jeopardize it. I'm sorry, Dave. I'm afraid I can't do that. I love that movie. Is there any truth to this popular science fiction plotline? Do we humans run the risk of creating machines that might eventually turn on us?
Well, it's a great question, of course, that it's very intriguing for all of us. I love that movie also, and you might remember that in that movie there were a lot of predictions like the iPad or objects like iPad, or for instance the capability of the computer of performing labial reading and so on and so forth. All these things happened, but the part concerning intelligence did not really happen. So do we run the risk of creating machine that can really think and can turn on us? Well, you could have asked this very same question, say, 50 years ago, and many scientists at that time would have answered that thinking machines were ready to appear. I mean, this is a real fact. You can check in interviews, but this didn't happen. So the truth is that the current artificial intelligence is not about thinking machine, and so we should not be afraid of that. It is about extracting information from data, pattern recognition, language processing, and many, many other things. So current AI is incredibly smart in doing these kind of tasks, but is not intelligent in a human-like sense. And in fact, nowadays, in order to discuss and to define intelligent machines, we use a different term. We call it artificial general intelligence and not artificial intelligence, to discriminate, to distinguish between what is going on today and what is, the kind of plot you might see in movies. So artificial general intelligence, I like to say that it is logically at an infinite distance. Okay? Still, there are wonderful things that are happening today. Predicting how AI is going to evolve is absolutely impossible, and I'm pretty sure that it will be different from what we can imagine. Reality is more creative than imagination, in a sense. So I think that a great deal of understanding will come from connecting, current AI and neuroscience, for instance, and so. I think that we will observe fantastic results coming out in the next years, but not in the sense probably of thinking machines. So in a very abstract sense, one might say that artificial general intelligence can become dangerous. After all, an intelligent machine would be better than a human, right? And so it would be difficult to control. But this is a kind of an arbitrary, abstract, worst-case view. Similar argument would hold for other scientific discoveries or tools or whatever. So once we put science and AI in a realistic framework, well, I would say that at the moment I cannot foresee any danger. On the contrary, so we should be realistic. We should avoid any misuse of current artificial intelligence. So in that sense, it is dangerous. I mean, we should avoid, military weapons and social control to be implemented through AI or things like that. But this is something different from, machines that turn on us. So there are very important issues related to digital ethics, for instance. But this is, true for science at large. It's the issue of the relationship between science and society. So rather than being worried about AI that can turn on us, I would be worried about climate changes.
You gave a TED Talk in which you stated that the term artificial intelligence, which dates back to the 1950s, you stated that there has been no significant progress since then. How is that possible with the enormous technological leaps we've experienced in the ensuing years? Are we only in the preliminary stages of exploiting artificial intelligence today?
Well, the progress in modern AI, which should be called machine learning, is in fact quite recent. No one was able to make a prediction about what was going to happen before 2010. So it's just, what is going on today essentially was started less than 10 years ago. Okay, so it's true that we are experiencing an exciting technological leap. It's true that something important is happening. However, it is in the direction of augmenting our cognitive capabilities. It goes in the direction of helping us in understanding the world and making sense of data, and therefore extracting and identified new discoveries across science, new applications, and so on and so forth. But it's not about really developing a thinking machine. This is something different. Okay, so in a sense, if you want to make an analogy between, say, artificial intelligence and the brain, it is as if we are developing a great visual system for science, but not a thinking cortex. Okay, so what we are doing now is just a great visual system. So you may have a visual system without intelligence, but in a sense you're right. All intelligent machine, whatever it is, an intelligent machine in your imagination, would need the visual system to interact with the world. So it is a necessary condition, but it's not a sufficient condition. Okay, so we are creating preconditions for, say, thinking machines, but we are still infinitely far from them.
Mm-hmm. And regarding these limitations of this visual system, in the same TED Talk, you spoke about the challenges of writing computer code for object recognition. And you gave the example of chair recognition. For example, if it has 4 legs, a flat surface to sit on, and a backrest, it's a chair, when obviously that is not an accurate description of many chairs we encounter in our daily lives. And in that sense, I understand that computers would, in fact, be blind to any chairs with an alternative form. So, although computers are superhuman in their capacity to study masses of data, can we say that they're thick when it comes to lateral thinking?
Well, actually, I think that computers are, in a sense, capable of lateral thinking, but this should be defined. Okay, so what computers do, what machine learning AI does, is to learn from examples, right? So, in a sense, the computer sees a lot of different chairs, and then it learns an internal representation for chairs, which allows the computer to recognize other chairs that it has never seen before. So would you call this a lateral thinking? Probably yes, within a certain domain. Okay, so this machine become good at making prediction just by creating an internal representation of the objects that it has, the machine has seen during the learning phase. So this is the so-called end-to-end learning. Computers build an internal representation of the objects they need to recognize, and this, if you think about it, is a great progress. So we are not anymore writing codes, for computers. We are letting the computer learn from reality. And this already has, fantastic implication. For instance, just last month, so it's a super recent result. DeepMind, which is, by the way, the company that was able to design an artificial intelligence program for playing the game of Go, which was considered to be out of reach for computers, you might remember, in 2016. But okay, so the very same company was able to solve a fantastic problem in biology. So to predict the structure of protein just from the sequence of amino acid. Now, this is a really great discovery, which will help, us in the design of new, us, I mean the community, in designing new proteins and drugs and so on. And scientists have been working for 50 years on this problem without, say, success. Now, by using, the data, AI device was able to learn some internal representation for this type of problem that allowed the device itself to predict this, to become capable of predicting the final structure of a protein just given its sequence of amino acid. And this is even if you're not expert, believe me that this is a fantastic problem, because the structure of the protein encodes for the function of the protein, right? And the protein are the bricks that make cell functioning. So what I would say is that for specific domains, machine learning, AI, can go wide in the sense that it can go beyond what is obvious for us in this sense. However, transferring knowledge across domains, say from chairs to protein, that's kind of difficult. In this sense, they cannot go wide. However, but I should say one last thing about this, which is very interesting. The neural network, the artificial neural network that DeepMind has used to do this application in molecular biology, which, by the way, could lead to a Nobel Prize, I mean, as far as I can see. But the neural network uses elements, architectural elements, that were designed in a totally different context, in the context of natural language processing. So something can be transferred. In particular, the methods, the architecture, the tools can be transferred. So what you learn in a field can be learned in an application field of AI can be transferred to other fields. But of course, you would not have a single neural network which is capable of lateral thinking in a broad sense. These machines are capable of generalizing within a certain domain in a non-trivial way. So whether you want to call it lateral thinking or not, we should decide. But it's really extremely valuable for research.
So you have mentioned, Riccardo, the predicting of the structures as well. They're very good at detecting anomalies, and they are used in this way for tumor research. Could you explain how that works?
Well, yes. The idea is that if you have clean data, so if you have a lot of data, let's say a lot of pictures of tumors, for instance, skin tumors, or a lot of mammographies, or a lot of NMR scans of the prostate for men, then you can train these machines to actually associate to each example a label which says, well, and this label has to be predetermined by experts, right? So the idea is that you can train this network to associate to given characteristics of the image. So, for instance, the presence of a dangerous anomaly to the fact that it is in fact a tumor or not. And so this machine, if you have enough data, then this machine can not only learn the example that you've used for in the training phase, but they can learn to generalize. And in this sense, they become a tool that augments the cognitive capabilities of a medical doctor, right? Because then you will be able to scan through millions of mammographies or NMRs or pictures of skin tumors, for instance, because this machine can run very, very fast. You know that they are very reliable and they have a high accuracy, so you can. It's a new technology that allows to the doctors to work in a different way. So I think this is for the benefit of everybody. I mean, you will still need a doctor to validate and to explain what's going on, but you can do it at a different rate.
And the computers elaborate this information through neural networks, which you mentioned. Could you explain to us how these neural networks work? And if they're capable of creating neural networks, that sounds to me like computers are not lacking brains. A brain is a neural network, correct?
Yes, the brain is a neural network. I mean, the analogy, the term neural network is a bit exaggerated in a sense. Mm-hmm. So there is an analogy between the components of these machine learning tools that are called deep neural networks or artificial neural networks, and there's an analogy between the basic elements of these networks and the real biological neurons. They are both nonlinear devices that collect inputs and then emit an output signal and so on. And so then they are arranged in certain networks that can be pretty complicated. So there is a strong analogy, but the way they function is, as far as we know, different in the sense that we know how artificial neural network works. There's an algorithm that, as you draw more and more examples, adapts all the connections in the network so that at the end your artificial neural network is capable of making the correct associations. On the contrary, the brain, we don't really know how it works, so it's difficult to say mm-hmm. if they are really similar. I think that there are issues that arise in machine learning that also arise in computational neuroscience, and this is a fantastic, field of research and of future progress, I think.
And what are some of these questions?
Well, one of the main questions is, for instance, how is it possible that you learn with relatively few examples in reality? I mean, a baby or you or us, we learn, but we don't need to see millions of chairs to mm-hmm. recognize a chair, right? We just learn with less examples. Or, how do you convey to a baby all the information that you have accumulated? So the current way machine learning works is by processing an enormous amount of information, but that's not the way we work. And so there must be a way of training these systems without having to use this massive amount of information, a more efficient way. And in fact, this is a field of research which is called Self-Supervised Learning, in which somehow these artificial systems try to make predictions about a model of the external world they are building. And based on their prediction, they'll correct the behavior and so on. And this looks similar to what's going on in babies. Because, for instance, in babies, it's very well known that, if a baby has less than 8 months, it doesn't have the notion of force of gravity. So if you show him a picture with a flying car, for him, this would be perfectly reasonable. But if you show the very same picture just two months later, when he is 10 months old, then he would be very, very surprised by seeing a flying car. Why? Because in that interval of time, between 8 and 10 months, he has developed the notion of force of gravity. So in his model of the world, things should fall down, right? And so he's always projecting his model, checking his model with respect to what's happening outside. And so there's the interaction between expectations and observation is what is driving learning. So, I'm being very generic right now, but there's a very interesting field of research at this interface. But in general, this is also the way AI is going to evolve. We cannot always just process an enormous amount of data. We need to have a more active approach to learning. And so this is a point of contact, but then there are many, many others. So it's not just this one. This is just one example.
Riccardo, let's zoom out for a moment. While you say that there has been no significant progress in artificial intelligence since the 1950s, you often cite the year 2012 as a fundamental year for AI development. Now, for those of us who remember, 2012 was an eventful year. There was talk of the end of time according to the Mayan prophecy. A NASA rover landed on Mars. Felix Baumgartner broke the sound barrier by free-falling 39,000 meters. And topically, a Middle East coronavirus was first identified. But what else happened that year that impacted your field of study?
Well, what happened is that a machine learning algorithm outperformed all other classical programs in the task of object recognition. So this might look as a very technical result, but it had deep consequences. The reason is the following, is that each year there is a worldwide competition in which experts in vision propose new algorithms for the task of detecting the presence of a specific object in a natural image. More specifically, the challenge consists in identifying the presence of one among 1,000 alternative different objects in a natural image. So, and each year you have this kind of competition, and all the algorithms have a certain performance, and you can rank them and see which are the best technologies. In 2012, the algorithm based on machine learning, on an artificial neural network that learned from a data set of images, got performance that were totally superior with respect to the other algorithm. And that event showed to the scientific community that machine learning was a new way of doing things. By now, the algorithms have superhuman performance on this task. I mean, algorithm based on neural networks can detect the presence of objects with an accuracy which is much better than human. So I think that we can say that 2012 is when machine learning, in the sense of deep learning, so of this complicated artificial neural network, took off like an airplane. So it started to fly. Since then, a lot of things have happened, because when you realize that a certain method, a certain class of tools are very effective, then you start to apply them in very, very different fields, and so there's been an incredible progress. For instance, a striking example, in my opinion, is natural language processing. There is the latest neural network that does this. It's called GPT-3. And so this is a neural network composed of something like 176 billion of parameters. So it's a huge device that has learned how to write by essentially scanning all the text that could be found on the web. And now this neural network is capable of writing, articles in a wonderful language, totally correct. And now, of course, you have to give to the machine some logic. I mean, you have to give some key sentences to make sense of what the network is going to write. Otherwise, it would just output some very well written nonsense text. But still, the way it writes, it's incredible. There is a very nice example on, I think, The Guardian. It's an article titled "I'm a Robot," and it's written by this machine, and it's incredibly well written. But you see, since then, machine learning since 2012 has been used in many different fields, and progress is sneaking, out in all sciences that use data. For instance, just to connect to your initial observation, a new antibiotic for Escherichia coli, for this bacterium, was discovered by using machine learning, and the way they did it is just by looking at a lot of molecules that had certain chemical properties, and by learning from them, the neural network was able to output a set of predicted molecules with antibiotic properties, say, and so they tested in the lab, and they found a new antibiotic which is very different from the others, known other antibiotics, and so bacteria have not adapted to them. And so I have a question for you. What is, in your opinion, how would you have named this antibiotic? Halicin, and HAL is the computer of a space odyssey.
Oh, fantastic.
That was no, but it's. I think it's amazing. I mean,
you beautifully linked us back to the beginning, Riccardo.
Yeah, that.
So, Riccardo, you've made it clear that AI can have nearly infinite applications. From your privileged point of observation, in what ways is artificial intelligence currently being applied to solve the messy problems the world faces today?
Well, it's kind of simple, by extracting valuable information from data in real time. And this will be crucial to deal with messy problems, from studying specific scientific issues like, say, in astrophysics, in economics, or in cell biology, but also in dealing with complicated problem related to society and to society. For instance, if you want to analyze the data that monitor climate changes, you would want to use these machine learning tools. So it's really whenever you have a lot of data that you cannot handle as a human being, and you cannot handle even by writing appropriate codes, because you don't really know what to look for, and therefore you need something that learns from the examples, then machine learning becomes useful. And also I think there is a very important aspect of AI. AI enables other technologies to become effective.
And what are the most relevant scientific challenges that AI is currently facing?
Well, AI still has to solve some fundamental problems, like the identification of causation patterns in data and how to improve unsupervised learning. So the issue is that at the moment, AI is able to identify even very subtle correlations in the data. But from that, to identify causation patterns, so causal mechanisms, is still there's still a lot to do, and building systems, artificial systems that from data are able to identify, somehow which is the law underlying the generation of the data itself is a field of research, and there's a lot of work going on. And then we need to improve all the techniques for the so-called unsupervised learning. So when the network have to learn from data without any input from humans, so without any pre-processing phase in which humans characterize the data somehow. This is because the vast majority of the data are of this type. They are so, these are so massive that a human cannot even look at them. And so here there's a lot to do, and this has to do also with what we discussed before, the idea of having efficient methods to interact with the data, so like modeling the data itself, making prediction and see what happens, and then correct the behavior. So there are many issues in these two fields, causation pattern prediction and unsupervised learning, that have a lot of conceptual impact. They will have a lot of conceptual impact because they are deeply related to the issue of how learning takes place, how high-level learning takes place, and also a lot of practical impact. I expect any progress in these two fields would lead to very concrete application. But I should also say one thing. When you ask me what are the most relevant scientific challenges AI is currently facing, I can tell you these very general topics, and I'm not mistaken. I'm sure that that's the case. However, every few months there are new discoveries coming out that have not been predicted by anybody. So somehow the way this field of research is evolving is a bit beyond our, say, imaginations. For instance, the result I mentioned to you about predicting the structure of proteins, which is a fundamental problem in molecular biology, the whole scientific community was very, very surprised when the result came out a couple of months ago. So nobody was able to predict that. So you see, it's kind of difficult to make a prediction about what's actually going to happen. Predicting is a very challenging. Making prediction is very challenging, and in particular, when you have to deal with the future.
Of course, AI is an absolutely fascinating Pandora's box, and I've really, really enjoyed discussing it with you.
Thank you very much, David.
I'm David Wayne Callahan, and this has been Clarity in a Messy World, a podcast from Bocconi University, Milan. Thanks for listening. You can find references from this episode in the podcast notes. To be notified when new episodes come up, subscribe to Clarity on Apple Podcasts, Google Podcasts, Spotify, or Spreaker.